All right, good morning, folks. I'm going to get started. We don't have a lot of time because it is a short day, and I'm going to give you a quick lesson. This lesson is from section 5.3 in the night book. We're going to be talking about three things today. We're going to be talking about weight, mass, and apparent weight, and how they're similar and different. This can be a little tricky at first, but I think it'll make sense to you really soon after we talk about it just for a little bit. So you should already know a little bit about mass and weight, but I'm just going to review with you. So mass is how much stuff is inside an object. The symbol is a lowercase m, and it's measured in kilograms. Weight is how much force gravity pulls on you with. And we don't know what gravity is yet, but we're going to learn about it soon. Seriously. Hello? I'm good until Mr. Knight gets here. All right. All right. I'm sorry. Bye. How much force, gravity, pulls down on you with. The symbol I will use in my class is a little different than what they use in the book. The symbol I will use is a capital F with a subscript capital W for the force of weight, and it's measured in newtons. And I'm not going over that because you should know what a newton is. It's a kilogram multiplied by a meter divided by a second squared. So the new thing that we're going to learn about today is apparent weight. So sometimes you appear to weigh more than you actually do. If you think about it, if you've ever been on a carnival ride, you felt this before. Like one of those whirligig things that goes around and around, and you feel like you're being pressed outside, and you're like, ah! Or, when they drop you down out of the sky, when you come falling down, you're like, oh my God, I'm going to hit the ground. And then the ride like grabs you and slows you down really fast down at the bottom. Where I grew up as a kid, they call it the Texas cliffhanger. They took you like 500 feet in the air in a box, and then they dropped you. And you're like, I'm going to die. And then you got down to the bottom, and then you felt like you weighed a whole lot when they suddenly slowed you down without killing you, which was the important part of the ride, that it didn't kill you. So those were fun rides when I was a teenager. I remember them very much. I don't know what they call it out here. Oh, you have the Tower of Doom at Disneyland, where the Tower of Terror. That's what it is. And you bounce up and down, and you're like, oh my God, I'm gonna die. And then when you get down to the bottom, it feels like as it stops, the seat is pressing up on you harder than normal, and then you feel like you weigh a whole lot. So that is the apparent weight. And apparent weight is what we're going to be talking about here. So apparent weight is how much force is required to support an object, and it feels, it feels like gravity, but it is caused by structural supports. Instead, the symbol that I will use, which is different than the symbol that your book uses, is capital F, lowercase WAPP. Looks like WAP. It's weight apparent, the force of weight apparent, and it's going to be measured in newtons. So now I'm going to work a couple little examples. So actually, just one example with you, because I don't need to make a long video, and I have to go really quick. In fact, I was supposed to have left already, so I need to hurry up. So let's think about a guy in an elevator. So here's an elevator. Yay, Mr. Williams and his drawings. Woo! And as one does in public elevators, this man brought his bathroom scale with him, like all budding young physicists might do. He takes his bathroom scale with him everywhere he goes. And so, unafraid of the weird looks that his fellow passengers might look at him with, this person stands in the elevator and on his bathroom scale, looking like he has lost his marbles. And let's consider this person before the person starts moving. So not moving. Okay, so if this if this gentleman is not moving, then let's say that the weight of gravity on this person would be, I don't know, an adult is like 950 newtons. So let's say it's a teenager is 850 newtons or 800. So let's say this person has a force of weight of 800 newtons on them. Well, by Newton's third law, there's going to be equal and opposite forces on the person. Let's draw a free body diagram here. So we've got the force of weight downwards. And we have the normal force from the floor not falling apart. You remember the normal force is caused by the floor not breaking. So we got the normal force pointing upwards. And the normal force is acting on the man, and the force of weight is acting downwards on the scale. So we have equal and opposite forces acting on different objects. And there we go. You also have the force of weight pulling, so you have the force of weight pulling down on the man, the force of the floor pushing up on the man, so those are balanced forces. And then you have Newton's third law interactions between the man and the floor. So I'm making a video. Okay, so let's consider what happens when it starts to move. That was a Carmex. It came flying.
Why are you throwing Carmex?
Yeah, because you're talking. Thank you, Trey. So let's say that it is moving. I wrote this down before. Let's say the guy is moving upwards. At accelerating at 4.7 meters per second squared. So this is going to look a little different now because he's not just sitting there in the elevator not doing nothing. Now he's going to be going. So I don't know if my artistic skills are up to me showing the excitement on this man's face when the elevator starts to move. Let's see if I can get him to try. So here he is. Oh, Okay, there we go. Yeah, that's art. That's all I have to say. So there he is, filled with astonishment. Yeah. I get hair helps. Yes. So definitely excited. The elevator is going upwards at 4.7 meters per second squared. Now, let's think about it. Is the guy going to weigh the same as he always did? Well, yeah, the Earth doesn't pull on him harder or less hard just because he's going up or down, so his weight doesn't change. Does it feel to the guy like he weighs more? Well, you betcha. Because now, like, the Earth's pushing up against the Earth. It's not really the Earth. The bottom of the elevator is pushing up against him and making him, like, speed up in that direction that he would not normally be going upwards. So he feels, like, weird. You can imagine. Now, most of the elevators don't do this because the federal government says that we are not supposed to kill little old ladies in elevators, so that they don't let them go too fast. But you can imagine if you had a souped-up elevator that went really fast, like from the first floor up to the 10th floor, like, 2 seconds. Yeah, that would be really cool, except your grandma might not like it. And you would probably feel like you weighed a lot when you went up in that elevator. So let's think about that situation. So the forces acting on, let's see. Let's think about the forces acting on the man for a free-body diagram. So the forces acting on the man, well, the man still has its force of weight, just like before. So like in my previous picture, he's got that same weight force downwards. But what about his normal force upwards? Is it the same normal force upwards that he had before or not?
Well, no, it's less.
It's hard. You only have 3 options. It's more or less or the same, right? So those are your 3 options. And if the normal force exactly balanced the weight force, there would be no net force on the man, right? Let's think about it logically. If the normal force and the weight force exactly balanced, there would be no net force on the man. And so then by Newton's first law, the only options you'd have are that it would move in a straight line without speeding up or slowing down, or that you'd be stopped. And that would be what you'd get if all the forces were balanced. Well, is the guy standing still or moving at a constant speed? No, he's accelerating. He's going upwards. Therefore, the man has a net force on him. And it's got to be going upwards. So is the normal force bigger or smaller or the same as it was in the previous picture? It has to be bigger than it was because in the previous picture, the normal force only had to counteract the man's weight. I'm going to say something important here. In this picture, the normal force only had to counteract the man's weight by Newton's third law. Here, that's not the case. The normal force has to counteract the man's weight, and it also has to accelerate the man. So part of the force is counteracting the man's weight, and another part of the force, which is bigger, does the acceleration part of the man. You can think about the normal force doing 2 jobs. There's the counteracting the weight bit, and there's the speeding you up bit. All right. So then my normal force is going to be a lot bigger. You can get really confused here if you're not careful. Let me explain how you can get so confused. You have to think about Newton's third law, action-reaction pairs. However hard the floor pushes on the man, that's exactly how hard the man pushes on the earth, right? But then why aren't my arrows the same length? It's because I'm not drawing a free body diagram for the man and the floor. I'm only drawing a free body diagram for the man. So Newton's third, I remember I told you this a long time ago when we first started about Newton's third law, that Newton's third law is tricky because those action-reaction pairs are on different objects. So the normal force on the man from the floor is balanced by an equal opposite force on the floor by the man. But I don't care about that when I make my free body diagram, because I'm not making a free body diagram about the forces on the elevator car. So there's a big old equal and opposite to the normal force pushing down on the elevator car floor. Yeah. But I don't care about it right now, because the only thing I care about right now is the forces on the man. So the man is going to have unbalanced forces on him. That's why he's going to be accelerating upwards when he's in the elevator car. But it doesn't violate Newton's third law, which can be quite tricky. All right, let's figure out the net force on the man. Let's use Newton's handy-dandy second law. So the second law says the sum of all forces, in this case it's all in the y direction, so let's just do it in the y. The sum of all forces in the y direction. Now, this is a tricky bit of Newton's third. When you add up all the forces, what do they equal to?
0. Oh, let's see.
Newton's law says sum of all forces equals ma.
Yeah.
Yeah, that's what it says. Newton's second law says that sum of all forces equals ma. So, what are the forces that are in my y direction? We got my normal force, so I'm going to scooch up a little bit. My normal force, and what else do we have in my y direction? My weight force. Okay. And my normal force plus my weight force is going to equal to ma. My normal force is, well, is this my actual, this is my actual weight, right?
Yeah.
So then my normal force actually counts as my apparent weight.
Get you added together.
So my normal force is going to be, in this case, my normal force is my apparent weight. And I really want to know what my apparent weight is. But before I go messing around with that, I need to think a little bit. So look here. These are in different directions, aren't they? So they should have different signs. Which one's going to be positive? The normal force, because it's up, see? So this is going to be positive. And then that means that, of course, that my force of weight has got to be negative. So then I'm going to rewrite this to be this. Force of normal minus my force of weight is equal to ma. And that works out because the force of weight is defined as being m times g, and g is always the absolute value of the acceleration due to gravity. So it doesn't have a negative sign associated with g, and you're going to need that negative sign in order for this to make sense in a second. So if you want to think about that at home, this will be on the video. That's kind of a tricky logic thing that I just did. So then the normal force, if I rearrange it with algebra, is going to be equal to the force of weight plus ma. Oh, wow. Now we can think about this logically. When the elevator was not moving, back in this picture,
Acceleration.
when the force of the force of weight and the normal force, they exactly balance each other, right? They 100% balance each other. So however much the Earth is pulling on me with, when the elevator is not moving, that's exactly how much my apparent weight is. My apparent weight is my actual weight. It appears that I weigh 800 newtons, I told you. And guess what? I actually do weigh 800 newtons when I'm not moving. So, or actually, same deal when I'm moving at a constant speed. So when an elevator is like moving at a constant speed, if you stood on your scale, then your scale would read what your actual weight is. Cool. However, now let's look here. When I'm speeding up, going upwards, then my apparent weight is going to be my regular old weight of 800 newtons plus some more weight because I'm speeding up over here, just like I told you before. So let's plug in the numbers and see how much this guy would weigh, or appear to weigh. So he's got his 800 newtons just from having mass inside of him. So having stuff inside of his body causes the earth to pull on him by a certain amount. For this guy, it's 800 newtons. And there's stuff I didn't do with you before. We didn't figure out how much mass was inside the guy yet. So let's do that over here on the side. I'll just make a little box. So if the guy's weight is 800 newtons and weight is equal to mg, my m looks sad, mg, then if I want to know m is going to be 800 newtons divided by 9.8 meters per second squared. Well, I can do that in my head, but I wouldn't be 100% right. So that'd be like 80 something, but I better do it in the calculator to make sure. So 800 divided by 9.8, yeah, 81.6, because I couldn't have done that in my head. So I knew it was about 80. 81.6, that'll be kilograms. So that's the guy's mass. And I need that now because in order to do the next part, I need his mass. So then it would be 81.6 kilograms multiplied by, what acceleration do I use? Am I going to use the acceleration due to gravity? No, I already accounted for that in my weight. Because gravity's pulling down on the guy. So that I use that to figure out this. What acceleration do I use here? That's right, so 4.7 is how much the guy is moving upwards in the elevator. So it's going to be 4.7 meters per second squared. So I don't know what that is. 81.6 times 4.7. That's going to be 383.7. So 383.7 newtons. And then we already have the 800 newtons that the earth pulls down on him with, for reasons of gravity that we don't know anything about yet in this class, but we're going to learn soon because I keep promising you I'll teach it to you. So then this guy's weight apparent, except I said I would say a W, didn't I? W, it should be WAP. That's a messy WAP. The force of weight apparent is going to be 800 plus 383.7. So that's 1183.7. 1183.7 newtons. The force of weight apparent. Is that more or less than his actual weight? It's more. So just by this logic, you can already figure out kind of like how much do you think he's going to weigh about as the elevator goes down? So if he was just minding his own business and the floor dropped out from him in the elevator, which would be entirely scary, and down with the elevator, boom! What do you think would happen to his scale reading? Yeah, his scale would appear like he's losing weight. It'd be the fastest weight loss program ever. It's got Jenny Craig beat, right? Because all of a sudden, bam, his weight could just like go to zero as he falls. All right, how to lose 100 and lots of pounds. That would be me. How to lose that in like 0.2 seconds. Of course, unfortunately, you gain it all back down at the bottom of the elevator shaft. So let's give you a homework assignment. Thank you for being very kind while I made this video for second period, since I can't be here for them today. I have some ones that look fun to me. I hope you have a good time with them. We don't have a lot of time today, but I'll give you two, and that'll give you time to play with one in class, and then have another one that you can mess around with at home today. So this will be page 156, numbers 20 and 21. I hope you have a good time with these. They're fun. I don't want to give you much. I don't want to give you more than this. I'm just going to give you this, and then you have your your worksheets from yesterday, and they're all due tomorrow.